Hello and welcome to the Open Heat Transfer course Conduction. This course is brought to you by a cooperation between the Aachen University and the University of Twente. My name is Wilco Roofs, and in this video we will show you the solution to the differential equation for fins. In the last video we have already looked how to derive the differential equation for fins, and we came up with the differential equation that looks like the part here on the top. The question is, how can we solve this differential equation, and is there a general solution to it? And of course, if we want to solve this differential equation, we have to deal with the topic of boundary conditions. So let's first review the differential equation for fins. How did we derive this equation here? So first of all, we looked at this infinitesimal element and we drew all the fluxes that are going in and going out. So differential element has two important sizes. So first it's the cross-sectional area of the heat. So this here I see at the end the fin, and we have the outer area here, the circumferential area or the perimeter on which the heat is transferred into the environment. So we have inside the fin the axial heat flux Q dot X that is entering the fin, and we have an axial heat flux Q dot X at location X plus delta X. And of course, then we have this convectional heat transfer, the flux by convection out of the fin to the ambience. This differential equation, or better said, this energy balance, which results from the balance of these three fluxes, will lead finally to the differential equation. But how can we solve this differential equation? So first of all, we have a problem because the differential equation is inhomogeneous. Why? We have here this TA, which gives alpha times u times TA with a negative sign, but this doesn't really matter. The most important part is that this is an inhomogeneous differential equation that we cannot solve so easily. And in order to have a solution approach, we will use the method of homogenization of the differential equation to get rid of this nasty little constant parameter. How to do that? So first of all, we have to define a new parameter, and we call this parameter theta, like the temperature difference. And this parameter theta comprises of the temperature of X minus the ambient temperature. And in this way, if we plug in the parameter here, we see that we get rid, of course, of this parameter that is a constant here. But what happens with the temperature d squared t dx squared? How can we replace this? In order to do that, we have to determine the first and second derivative of our definition here. So we take really this definition, derive it by the first time, and we have the theta dx is equal to the first derivative of the temperature because the constant just drops out. The next step is even simpler. We have to take the second derivative, and then with just to make from the first derivative to the second derivative, it's a very simple task. There's nothing to drop or think about. Now, we can use this theta, the definition of theta, to plug it into our differential equation. What happens then is that we have simplified our differential equation quite a bit because we have gotten rid of this constant parameter, and now we have a homogeneous differential equation with a single parameter that determines this problem. And we call this the fin parameter, and we will not call this parameter like m, but we will give it an m square because of later easiness to calculate the fin problems. So we just combine all these four quantities, the heat transfer coefficient, the circumference of the problem, the cross-sectional area, and the thermal conductivity to the fin parameter. And now our differential equation is very universal already. What does the fin parameter tell us, or how can we determine this? So let's look for the fin parameter. What is it determining? Of course, it's thermal conductivity of the fin, as we have said before, two geometric parameters, and the heat transfer coefficient to the surrounding medium. If we look now for two exemplary fins, for instance a pin fin, the perimeter of this pin fin is the perimeter of a circle, so it's PD, and the cross-section area of the circle is PD squared by 4, so we can easily calculate the fin parameter m squared is equal to 4 alpha divided by lambda times d. Another type of fin geometry is, for instance, here a plane fin, where the fin is along here, and for calculating that, we of course need to calculate the perimeter, which is 2 times the thickness of the fin times the length, so that times the depth here, t, and the cross-section area is the thickness times the depth. And if we calculate m squared, we have on the top this delta plus t, and on the bottom delta times t. And because usually the depth here is much larger than the thickness delta, we can reduce the part here on the top so that we can simply, that the delta can drop out here, and then the t also drops out there, and the fin parameter becomes 2 alpha divided by lambda times delta. So I think there's a little mistake. I will correct for that. Please excuse. Now, the derivation of the general solution, now if we have this fin parameter here, if we have the fin parameter and we have the differential equation, now how do we solve this? Of course, we first need an ansatz. We need to know what type of function could be the correct one for which the second derivative of the function is equal to the function itself times some kind of parameter. Now, from math, we know that if we take the differential from an equation, it usually changes quite a bit. But there's one equation type that does not change so much, and that is the exponential function. So taking the first derivative of the exponential function remains to be the exponential function, and the second derivative also remains the exponential function. So let's try to use the exponential function as a solution. So we just say our parameter theta, so our temperature difference, behaves like the exponent of length, of a parameter s times x, what's our location and spatial coordinate. The second derivative of that is simple. It will be s squared times e exponent times s times x. Now we can plug this in, these two information here, and then we get the solution that s squared times the exponent of sx minus m squared times the exponent of sx is equal to 0. And this has to be fulfilled for any location x. And it seems to be not so complicated because we can cross out here the exponent by sx. And because this here can be any kind of variable, this has to hold for any location x. The parameter here in front needs to be 0 in order to fulfill this equation. So we directly see that S can have two solutions. The one solution is the square root of m squared, but one's positive, but it can also be the negative square root of m squared. So, and because we have two different possible solutions, we now construct our solution for the temperature by using both of the solution approaches. So once the positive S1x and once the negative, so this S2x. And we introduce the two coefficients c and d. And from that, it happens that our solution for the temperature will be some kind of coefficient times the fin parameter times x plus another constant times the exponent of the negative of the fin parameter times x. So we have now constructed one possible solution for the fin equation. But it is not the only possible solution because there are other equations that also fulfill this. But please note that this is not valid here for x equal to, this needs to be valid for any kind of location. I've told that already before. Sorry for that. But now, there is another equation that also fulfills it. Which equation is this? There's another one that has the ability to show that its differential is very similar to its own function, and that's the sinus or cosine, so those trigonometric functions. And especially the sinus hyperbolicus function, if we take the derivative, it will be the cosine hyperbolicus function, and the second derivative will again be the sinus hyperbolicus function. So this function would also fulfill our requirements. And interestingly, as you can see here, there is a mathematical transformation that allows us to go from an exponential function to a sinus hyperbolicus function. And if we see this part of the exponential function here, it looks really much like the two parts of the equation. So maybe it's possible to transfer that. And to do this, we also have to look at the cosine hyperbolicus function, which is in its definition very similar, but just we have now a plus here in between. So we have two types of general solutions for this thin differential equation, and it's usually that people have like some kind of feeling which they like more. So for my purpose, I always liked more to work with the exponential function, but I know colleagues who like more to work with the sinus hyperbolicus function. It's more or less up to you what you like to prefer. The solutions are identical because we can also transfer them. So we have the two coefficients a and b for the one function. We have the coefficients c and d for the other function. And we can translate the coefficient c to a and b, and d is also can be expressed by b and a. So that's just what type of solutions we can think of. Now, the next part is if we use the sinus hyperbolicus function, where we have like the coefficients a and b, and we have the exponential function. These two functions have two unknowns. And the reason that it has two unknowns is because our differential equation here on the top is of second order. So this just means that we need two boundary conditions to solve this problem. Either to solve for a and b or to solve for c and d. What type of boundary conditions can we use? So usually for fin problems, we define boundary conditions on the base. So this is here at the location where the fin is connected to the part, and on the fin head. But there can be also special situations because it is not the fin base which is important to start with the calculations. It can be if you have, for instance, a fin that is insulated here on the bottom part, so there is no heat transfer occurring here in this part, then your location here will be the base, and it's actually the location where the heat starts to be dissipated towards the environment, not necessarily the location where the fin is attached to the body on. Now, let's talk about the boundary condition here at the fin base. So we prescribe a temperature T base, and from that we have our parameter theta, which is T base minus TA. The other boundary condition is a boundary condition at the fin head. There are multiple options for that. One option would be that the fin is very long. So for that, we can assume that the heat that is transferred from the outside here, from the circumference, is much larger than the heat that is transferred here on the tip or at the top of the head. And from that, we can assume that the heat loss at the head is zero, so there's no heat flux, which translates to the fact that the gradient of temperature at the location x equal L is equal to 0. Another option would be that the area of the head is much smaller than the area of the surface. It's basically the same explanation, and for that we also see that the head has zero heat flux and the first derivative of the temperature is equal to 0. So they are really identical. Another option is that the heat on the head is not equal to 0, or the heat that is transferred at the head. And in this case, we might need an equation that describes the heat transfer from the head to the environment. And we can basically also use the same equation we used before. We just say there is a heat transfer coefficient, there is an area of the fin head, and there is a temperature difference. And let's just assume that the temperature difference is also related to the ambient temperature TA. So this is another option for a boundary condition for the fins. But now, how to solve the differential equation? We have here our differential equation, the first derivative and the differential equation itself. And now we need to plug in the boundary conditions. And let's say the first boundary condition is the temperature here at the fin base. And so the theta at the location x equal to 0 is theta b base. And we can now use this equation, plug in the x equal to 0, and we see that this becomes fairly simple. So the theta b is equal to the combination of c and d. So one of the coefficients c is equal to theta b minus d. Now the second boundary condition, let's assume that there's no heat flow at the location x equal to L, which allows us to use the second and the first differential. So we say that the heat is 0, that the first differential of the temperature, or also the first differential of our temperature difference, will be 0. And we can plug that in right now, and we can then have a second equation for our two unknowns c and d, and we can use the first definition, plug that in into the equation. And now we have the equation where the only unknown parameter is the constant d, for which we can resolve for the constant d. And if we know the constant d, we can also have an equation for the constant c. Now we solved our differential equation. We solved the two boundary conditions, or we plugged in the boundary condition to solve for the two unknown constants. And on that side, we are nearly finished in solving our problem, because now we have to add or include our definitions c and d in the differential equation. This is now a little bit of math, so just plug it in a simple way, and then reformulate and do some simplifications. I don't want to go into the details. The equation that comes out here is also given in the book of formularies. I just want you to know how to derive it, and maybe even in a question in a later task, you need to derive this question by equation by yourself, maybe for even different boundary conditions. As I mentioned before, we have two different formulations. We can either use it with the exponential function, or we can calculate it with the cosine hyperbolicus function. Now, how does the temperature profile look like here? Let's assume that the temperature profile here is given by the equation, and now we have to draw this. I think for you it might be very difficult to draw the equation based on the draw the temperature profile based on the equation to directly see what happens. But let's just do it by some kind of gut feeling. So of course we have here at T base the highest temperature, and we have the highest temperature gradient to the environment. So this means that the highest loss of energy towards the environment will be here at this location, and then it will be reduced because the temperature reduces it as well. And so what we expect is this exponential decay of the function as represented here by the equation. And then we assume the adiabatic head, so there will be a 0 gradient at the location here. And so this will actually be our temperature distribution inside the fin. Now the question is, do we reach the ambient temperature here on the top, for which we assume that there is no heat flux? Let's use the equation to answer that question. Is the head temperature TH equal to the ambient temperature when the heat loss at the head is equal to 0? We would imply that because the heat loss means that there's no temperature difference. But the heat loss being equal to 0 can also mean that the area is just very small. So let's plug in the value at the location x we at equal L into our equation, which reduces the equation, or it simplifies it very much, because we have the exponent by 0 plus the exponent by minus 0. This is each is 1, so we get a 2 out of that. And on the bottom side, we also get the combination of the two exponential functions, which we don't need really to evaluate. But what we see is that this value is not 0. So we do not approach this value here. So the conclusion is that even with the assumption that there is no heat flux occurring at the fin head, there is still a temperature difference between the head of the fin and the ambient. We don't reach that, we only approach this temperature, even for a very long fin. So now, finally, at the end, I would like to give again a few questions of understanding. So which approach can be used to solve this inhomogeneous fin differential equation? And this is approach of making the inhomogeneous differential equation to a homogeneous differential equation by introducing a temperature difference theta minus, or theta of x minus the constant value. And we cannot only use this here, we will use this later also in cases when we have an unsteady temperature distribution. So please keep in mind that this inhomogeneous differential equation can be brought into a homogeneous differential equation by using such a smart temperature difference. Next, which quantity influences the fin parameter m? So this fin parameter is influenced by the outer heat transfer coefficient, which describes how much heat is transferred from the fin towards the environment, and the two geometric parameters, one's the circumferential area or the perimeter, and the other will be the cross-sectional area of the fin. And last but not least, also the fin material makes a difference, so the thermal conductivity of the fin is an influencing parameter. Last question, which common boundary conditions can be used to solve the fin temperature profile? And common boundary conditions, I think, are prescribed values at the head of the fin and on the bottom of the fin. It can be a prescribed temperature on the bottom. It can also be a prescribed heat flux on the bottom. And on the top, we usually have or can use the assumption that the heat transferred by the tip is equal to 0, the heat flux. But we could also use a condition where there is still a heat flux driven by a temperature difference and a heat transfer coefficient on the tip. And with that, I would like to thank you for your attention. It was a little bit a long lecture this time, but I think it's important and it is a little bit mathematical, but please watch it again. It's a very important part also later for the tasks that we will give you. Thank you for your attention.